Okay, this is an example problem of a mechanics. It's an example of solving a mechanics problem for mechatronics. In this example, it looks like we're given a sort of a portion of a robot base. It's got these omni wheels, some kind of pressed stamped steel platform. I've got a diagram below. I might call it sort of a free body diagram. Here I've taken this as just a single body, supported the chassis. Read the question. It says you are designing a robot omni-wheel drive system. The shaft diameter is 3 millimeters. Looks like that's the shaft diameter. The length is 25 millimeters. Looks like that's the length from the wheel center. Here's the center line to the entering the motor. Let's see, the motor gear head is here. So it looks like I'm fixing the motor. I'm fixing that to ground. So that's the distance. The motor gear head has a stall torque of 5 Newton meters. Doesn't look like that's really shown since it's fixed on ground, but I'll write it down as 5 Newton meters. I guess that would mean I could apply 5 Newton meters of torque to that shaft. The mass of the robot is supported by a single wheel shown is 2.75 kilograms. So that'd be the mass. The shaft material is 6061 with a yield of 241 megapaw and an ultimate strength of 29 megapaw. What is the factor of safety in the shaft design, assuming a max shear stress theory? That's the one we've talked about. And assume the motor is not engaged. Well, if the motor is not engaged, I'm not transmitting torque, so I can ignore that. I need the max shear stress theory says I either compare my stress, my normal stress, to the yield divided by my safety factor, or I compare my shear stress to the yield over 2 times the safety factor. And that's from our notes. And I did that wrong. This is the strength. Stress on the left, that's the loading conditions. Strength, that's the material conditions on the right. They're two different things, okay? I said that wrong, but that's the way it should be. And it's the yield strength that we look at in this shear stress theory, max shear stress theory. Well, in our case, we don't have a torque. We have we don't have a shear stress. We have a stress. It could either be axial or bending. Turns out the stress is in the same direction, but they caused by different things. This one appears like it's bending. So I have bending stress. I need to calculate. I'll put a little B there. From our notes, we see the bending stress is given as my over I. My M is this force mg acting at a distance. My y is going to be the diameter halves, and my I is going to be about the cross section. Maybe that's called x, and it's given in the notes. For a circular shaft, Ix is pi over 4 r to the 4th, or d halves to the 4th for a circular shaft. So I can put all these values in. I get F dot L dot L is d halves times y d halves. Divide that by pi over 4 times r, that's again d halves to the 4th. Start putting in those values. I get 2.75 kilograms times 9.81 meters per second squared times the length. That's 25 millimeters. I'm going to convert to meters times d halves, so that 0.003 over 2. And the numerator, that's going to give me kilograms meters per second squared times meters squared. This is just a Newton right here. In the denominator, I get pi over 4. D halves is 0.003. That's our shaft diameter over 2 to the 4th. That would be meters to the 4th. So I'm going to get Newton meters squared over meters to the 4th. That's going to give me Newton meters squared. Newton over meter squared, which is a Pascal. All right, let's put in those values. So I lost my pen. Okay. So I get 2.75 times 9.81 times 0.025 times 0.003. Yeah, that's all my numerator. I divide that by my denominator, pi times 4, divide that by 0.0015. I'm going to divide 3 in my head, so I don't have to use parentheses. Got to raise that to the 4th. And it seems pretty large. Well, I see we forgot to divide that 0.003 in the numerator by 2. Get carried away. Could just divide this result by 2 if you're okay with that. Double checking 3 times 4 should get that divided by 2. 254. I think that's my right answer. Let's try it one more time. 2.75 times 9.81 times 0.025 times 0.003 divided by 2. That's what I forgot. Now I've got to divide by pi times 4 divided by 0.00. I'm going to now divide this 2 in my head, so I don't have to use parentheses. I'm not very good at this calculator. Okay, I got the same answer twice. So I'm feeling good about that. 254. So I get 254,435. I get 254 0.435 e to the 6th, or 254.4 megapascals. Okay, now I'm going to plug it into my max shear stress theory. I need to calculate factor of safety. So my N is going to be my yield strength over sigma. My yield strength was given as 241 megapa over 254 megapa. Now, are you seeing something here? I'm going to guess say factor of safety less than 1. Not a good start here. Makes me think I should double check my equations. That would give me a safety factor of 0.941. That's not good. That's designed to fail. That means in this condition, my shaft would yield, not break, but it would plastically deform. It would bend. So this is bad. I've kind of double checked my numbers, but I think we'll call it good. I mean, I guess at a minimum, you'd want N to be greater than or equal to 1, depending on the standard, depending how certain you are with things and the standards. Typically, we'd like to see an N maybe greater than 2. I mean, I guess if I were designing this robot, I'd have a minimum of a factor of safety of 2. But anyhow, that's the number that I've given these set of parameters. They ask for the safety factor, and that's what it is. Okay.